Okay, so what we're going to talk about now is we've talked about how the derivative gives you the slope of the tangent line at a point. So we've talked about the derivative at a point. So there's some issues with how we've been calculating the derivative, and let me explain what I mean. Let's go into writing mode. Okay, that was a fail. There we go. Okay, so let's say that you want the Okay, computer. Let's say that you want the derivative at 2. What you're going to have to do is the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 all divided by delta x. Right? Does everyone recognize, we talked about this last time, this is the difference quotient definition of the derivative at the point 2. Now, let's say you also want to know the slope of the tangent line at 5. That means you're going to have to calculate the limit as delta x goes to 0 of f of 5 plus delta x minus f of 5 all over delta x. Now, here's my question to you. Let's suppose that you have already calculated the first limit for finding the derivative at 2. Will this help you to calculate the derivative at 5? That's my question to you. So if you've calculated that first limit to find the derivative at 2 or the slope of the tangent line at 2, will that help you for calculating the derivative at 5? What do we think? Like, you have those two limits there. Are these two limits connected to each other? The ones that I'm putting in. Like, if you know how to do, if you've calculated this one, is that work necessarily going to help you with this one, is my question. Just put it into the chat. What do you think? Yes or no? And, like, you don't have to worry about being right. Just go with what your gut feeling is right now. Okay, so for the people who have had the courage to answer, the correct answer is no. It's not going to help you, because let's just say that you're working on, I don't know, let's just come up with some super easy one. F of x equals x plus 5. If you calculate f of 2 plus delta x, that's going to be 2 plus delta x plus 5. But if you do f of 5 plus delta x, that's going to be 5 plus delta x plus 5, which is going to give you delta x plus 7 versus delta x plus 10. Like, all the little details of everything that you calculate are going to be slightly different, and it's not really going to help you. So the real issue with what we've been doing so far is that each time we calculate a derivative, it's a whole new limit calculation. So if you wanted to calculate if you wanted to find the slope of the tangent line at 5 different points, you would then have to do 5 different limits. And that sucks. Does everyone get why that sucks? Like, you'd have to do 5 different limits to find the slopes of the tangent line at those 5 different points. That could take you forever, right? Because each of those limit calculations is sort of long. Okay? So what we're going to do is we want to speed up this process. Okay, so I'm just going to write that we are not happy with this idea that if you wanted to calculate the slope of the tangent line at 5 different points, it requires 5 different limit calculations. How can we speed this up? And it's actually a pretty genius idea about how to speed this up. So what you do is, instead of saying, hey, the derivative at some point a is equal to the limit as delta x goes to 0 of f of a plus delta x minus f of a all over delta x, and plugging in that particular number. Instead, what you're going to do is leave a variable x so that you can plug the number in later. Leave x as a variable so you can plug it in later. So instead, we're going to calculate the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So how is this different? Well, for this one, wherever you had an a, you plugged in an actual number in the previous way of doing it. Now, the x stays as x, and you actually get a function called the derivative that you can then plug numbers into it, and it will just tell you what the slope of the tangent line is there. So we'll do a super simple one, show you how this works. Actually, let me leave this on the screen for a moment in case you want to write it down. Take a swig of coffee. Okay, so let's do an example. Example: find the derivative function of f of x equals square root x, and then calculate derivative at 1 and derivative at 2. So previously, if we wanted to calculate derivative at 1 and derivative at 2, those would have been two different limit calculations. Now what we're going to do is find this function that we're going to call the derivative, f prime x, doing one limit calculation and then plug in 1 and 2 later. So how does this work? Like I said, we use the difference quotient definition. We're going to do the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So we plug everything in. We're going to do the limit as delta x goes to 0 of, now f of x plus delta x is the square root of x plus delta x, minus f of x is minus square root x all over delta x. So notice my first step is literally just plugging in what f of x is. Okay, now we can't just do direct substitution. Why not? Why can't we just direct substitute this and get our answer? Yeah, it's undefined when you plug in delta x equals 0. So what you notice is, well, we have a square root x plus delta x minus square root x all over delta x. So we're going to multiply by the conjugate to simplify this. So we're going to multiply by square root x plus delta x plus square root x all over square root x plus delta x plus square root x. Let's change the color. So on the bottom, you're going to get delta x times square root x plus delta x plus square root x. Okay, now on the top, when you multiply them, you're going to get x plus delta x minus x. Notice the x's are going to cancel. And you're left with an x on top. And I'm sorry, a delta x on top and a delta x on bottom times square root x plus delta x plus root x. And those delta x's now cancel. leaving me with 1 over square root x plus delta x plus square root x. Okay, so what we started with was this, that I'm boxing. That was our f of x. And what we're ending with is this. This is our g of x. And we know that f of x is equal to g of x, except when what? What can you not plug into f of x that you can plug into g of x? Yeah, delta x is equal to 0. Because if you plug delta x equals to 0, you get 0 on the bottom of this one, undefined. That's why you couldn't use direct substitution. But you can actually plug that into g of x. So these two functions agree except at a point. And when two functions agree except at a point, their limits are equal to each other. Which is why now our original limit problem can now be solved by instead calculating the limit as delta x goes to 0 of 1 over, and what we got down there was square root x plus delta x plus square root x. And now we can actually just plug in delta x equals 0, and we're going to get 1 over x plus, now the delta x is going to be equal to 0, then plus square root x. So now square root of x plus 0 is just square root of x, which means on the bottom we end up with 1 over 2 root x. And that is our derivative. If you wanted to find the slope of the tangent line for this function at some point, just take the point where you want the slope of the tangent line and plug it into that formula. You can just now use this to plug in any number you want, as opposed to having to do a limit calculation for each one. So I'm just going to pause for a moment. So like, if we want to find the slope of the tangent line at 1, we just plug into this function. You get 1 over 2 root 1, which is just 1/2. Apparently the slope of the tangent line at 1 is 1/2. If you wanted to find the slope of the tangent line at 2, you just now plug into this function, 1 over 2 root 2. Boom. That's the slope of the tangent line at 2. It's just now an easy thing of plugging into that formula. So I'm going to pause for a moment, and I want to know if there are any questions about doing that, like what I did.